If you sit perfectly still and watch a pendulum swing, you expect each second to match the last. We navigate our everyday lives assuming that time ticks away at the exact same rate for everyone, everywhere. If you take that timer and set it in motion, the moving clock will actually tick slower than the stationary one. Physicists call this time dilation, a measurable stretching of time between two observers moving relative to each other. This discrepancy occurs because of a strict physical rule governing our universe. The faster an object moves through space, the slower it moves through time. Walking down the street or even driving on a highway, the effect is so microscopic that your body never notices it. To actually record this shift in a human, you have to push them to extreme orbital velocities. Cosmonaut Sergei Krikalev spent over 800 days orbiting the Earth at roughly 17,000 miles per hour. By the time he returned to the ground, his high-speed journey meant he had literally traveled 0.02 seconds into the future relative to everyone he left behind. We experience time as a rigid, uniform background ticking away in the cosmos. In reality, it is a highly flexible fabric directly manipulated by physical velocity. To see exactly how velocity bends time, we need to bypass the mechanical gears of traditional watches and build a theoretical device called a light clock. The mechanics are simple. A single pulse of light bounces vertically between two parallel mirrors. Every time the light hits the bottom mirror and completes one round trip, the clock registers one tick. Now, place an observer standing perfectly still inside a high-speed transparent glass train and give them this light clock to hold. To the observer inside the moving train, the clock functions perfectly normally. The light continues traveling straight up and down between the mirrors. Within any single consistent frame of reference, meaning the local perspective of an observer moving at a steady speed, the laws of physics and the flow of time always appear completely normal. Watch what happens when we shift our perspective to a stationary observer standing on the platform, watching that glass train zoom past. From the platform observer's perspective, the light inside the passing clock must move forward continuously to keep up with the moving mirrors. Tracing this zigzag path covers a measurably longer distance than the simple vertical up and down path seen by the passenger inside the train. Notice how this diagonal path forms the hypotenuse, the longest side, of a right triangle created by the train's forward motion. Here we hit the universe's ultimate limiting rule. The speed of light is absolutely constant. It never changes, regardless of who is observing it or how fast they are moving. This creates a logical paradox. The light in the moving clock is traveling a longer distance, but it absolutely cannot speed up to make up for the extra length. Because that light must cover a longer distance at the exact same speed, each tick of the moving clock requires more time to complete. This inescapable geometry proves that, relative to the platform, the moving clock is literally ticking slower. In 1971, researchers proved this physically by placing highly precise clocks on commercial airliners and flying them around the world. When the planes landed, the traveling clocks had measurably lost fractions of a microsecond compared to the clocks resting on the ground. The geometry of moving light dictates a strict universal trade-off. Spatial velocity must steal from temporal velocity to keep the speed of light constant. If we move from hypothetical trains to the actual orbital environment high above Earth's surface, this physics lesson becomes a daily engineering problem. The navigation satellites circling our planet are moving at extreme orbital velocities relative to the people using receivers on the ground. Because of this extreme velocity, their onboard atomic clocks, devices that track time by measuring the hyperstable vibration of atoms, physically experience time dilation. To complicate the math, the reduced gravity in orbit actually speeds up the flow of time. These two forces create a complex competing cosmic drag that continuously warps the satellite network's internal clocks. To keep the network synchronized with receivers on Earth, physicists must continuously apply complex relativistic math corrections to the orbiting clocks. If engineers ignored this math, location data on our personal devices would drift by several miles within hours, rendering global navigation useless. Every time you route a trip on your phone, you rely on the elasticity of time. The equations of relativity act as the invisible blueprint keeping our entire global navigation infrastructure intact.